Okay, so first of all, I welcome one and all for this week's Wednesday colloquium and thank Manoj for putting this all together. So we are absolutely happy to have one of a young starter in the community of magnetic resonance and doing a lot of dynamic nuclear polarization to visit us in India from New York University Abu Dhabi campus. So Professor Asif Iqbal actually has his roots strongly in um, NMR spectroscopy for a long time. He was one of the first batches of BSMS students who graduated from Aizer Mohali. And I think it was the first batch. Second batch, maybe. Yeah, okay. And during that time, in 2011, Asif actually visited us and did a VSRP with Professor Hosur during the NMR group when they were at the peak of solving protein structures and things like that. Asif then went on to do his PhD from Aarhus University in Denmark. As kind of award-winning PhD thesis with Niels Nielsen, one of the leaders in solid-state NMR. And this is where I think sort of during the similar time, Professor Madhu here was setting up some of the solid state work from TIFR, and there was a connection, I guess, with Asif during that time. Madhu is, of course, here in the Zoom meeting. So thank you, Madhu, for attending. After that, he went to University of California, Santa Barbara, worked with Song-Hee Han, and with Song-Hee, continued to do a lot of NMR work, of course, and with a short postdoc with Mike Wasilewski, who is one of the leaders in transient EPR, photo-induced effects in molecular systems. Once he finished in Northwestern for a year, he came back and started his independent work in 2022 at NYU Abu Dhabi. Today he's going to share some of the very exciting results that he has in dynamic nuclear polarization, but he has strong interest in EPR spectroscopy as well. And he actually won a Young Investigator Award from the International EPR Society very recently. So I welcome Asif back to your VSRP Institute. So thank you for coming here.
Thank you very much. Am I audible? Okay. Thank you very much, Professor Jyotishman and Professor Manoj, for arranging this. Today, I'm going to talk about spin hyperpolarization in magnetic resonance. And this is a very special topic for me, especially giving this talk in TIFR, because I learned the basics of these techniques at TIFR with Huzur and with Madhu. So everyone would have seen the NMR spectrometer. This is how it looks like. And this is kind of a schematic for MRI. These techniques, they use radio frequency wave for detection. But these techniques in their present form, they're not very sensitive. So my research is about how we can improve sensitivity of these techniques using a technique called spin hyperpolarization. And for that, one has to have some add-on to these techniques. Okay, so one of the add-on that you see here is basically a source of microwave. So if one wants to improve sensitivity of NMR, one can have microwave along with electron spins. One can also do laser irradiation and improve the sensitivity. In my research, training, I have learned about NMR or nuclear spins, electron spins, and little bit of optics. And my idea is to combine these three techniques to improve the NMR sensitivity. We all know about spins. So they are like gyroscope. So spins comes from the intrinsic property of matter. There is an intrinsic spin, which leads to precession in a magnetic field. For the simplest case, there can be two energy levels. We call them spin up or spin down. And NMR or MRI, EPR, all these techniques, basically these techniques involve probing a transition from one energy level to the other energy level. So I'll give you one example of how MRI is done. So in human brains, in body, there is a lot of water molecules, and the hydrogen atoms, the nuclei of the hydrogen atoms, they have spin, which means when these things are placed in a magnetic field, those spins, they precess. And what we do in this technique is basically we excite the spins, and it leads to coherence generation. That is something we measure in time. Depending on the technique, the interpretation of this signal can be different. In the case of MRI, we mostly interpret how fast is the decay of the coherence. And that leads to the mapping of structure, function in our body. So spin-based techniques, they are very important. They are everywhere. But they come with one major intrinsic limitation, which is sensitivity. So the sensitivity is very, very low. And the reason is the energy levels that we probe in these techniques is very small, very tiny. And from Boltzmann factor, you would know that the polarization or the population difference between the two energy levels is also very small. For the case of NMR, the sensitivity is so low that if I have 1 million molecules, only 1 out of 1 million molecule effectively is giving rise to signal. So the sensitivity is the real challenge in the case of NMR or MRI. And it has many consequences. So when it comes to MRI, the diagnosis is always at the late stage. It takes a long time. If someone goes into MRI scanner, it would be 30 minutes or more than 30 minutes that one has to be in the scanner to get the MRI image. And that's basically because of sensitivity. In the case of, for NMR, there are many materials which in principle can be probed with NMR, but we cannot probe them just because of sensitivity. And if one wants to distinguish the signal from surface compared to bulk, NMR is not a very good technique in the conventional form. That is because the number of atoms or spins giving on the surface is a lot less than bulk. So, and many times it may happen that one has to measure NMR for several days, especially if it is a protein or insensitive material. You might have to measure 2D NMR for a week or longer than that. So these are the challenges, and my research is about overcoming these challenges. Similar to NMR, there is another technique. It's called EPR or ESR, electron spin resonance. And the fundamental physics is very same. We have again energy levels. The difference is the energy gap in the case of EPR or electron spin is 3 orders of magnitude larger than nuclear spin. Because of which the population gap, the Boltzmann polarization or the population gap is also a lot bigger in the case of electron spin compared to nuclear spin. So the idea of this technique, dynamic nuclear polarization, is to transfer this large polarization from electron spin to the nuclear spin. And of course, if you want to do a transfer between two different spins, they have to be coupled. So if we have a scenario where electron spin and nuclear spin, they are coupled, it's possible to transfer the sensitivity of electron spin to the nuclear spin. There are many ways of doing this transfer. One of the most common way is to irradiate microwave on the electron spin. And if one does it in the right way, it's possible without increasing the energy gap for the nuclear spin, it's possible to have a high polarization or the population gap in the nuclear spin. And so this technique is called microwave-induced dynamic nuclear polarization, and it can improve the sensitivity by a factor of, by orders of magnitude. This means that if someone can achieve a sensitivity of 1000, it means that whatever measurement that one would do with a conventional setup, if it takes 1 day or longer, with DNP NMR, it can be done in a few seconds. So this is what we want to do. Depending on where do you want to apply this technique, whether you want to apply this technique for MRI of a solution state NMR or for solid state NMR, the technique can appear different. Yes.
Water proton. Yeah. Are you thinking of a paramagnetic metal with a coordinated water proton? Like, is it distance dependent, or is it like what is the nature of the coupling?
So the coupling is definitely dipolar coupling, and it is, of course, distance dependent. So if there is a nuclei within 1 nanometer around the electron spin, the DNP transfer can happen to that nuclei. So a coupling within a distance of 1 nanometer. It also depends on nuclei. If it is proton, you can do it at longer distance. If it is carbon, because carbon has smaller dipolar coupling, the distance has to be shorter. So depending on the dipolar coupling effectively, if the dipolar coupling is large enough, one can do the transfer. But there is one more trick. There is one more point to it, which I'll come in my later slides.
What do you mean by the transfer? What is it doing exactly?
What exactly it's doing, it's my upcoming slides.
Okay.
So you don't have any coupling when there is no microwave shining, right?
So even if there is no microwave, there is some dipolar coupling. There are two spins. Each spin, they have their magnetic field. They have a magnetic moment. So there is a dipolar coupling even if we are not shining microwave. When we shine microwave, we want to do the transfer of polarization. What it means, I'll come to that in my later slide. But we want to do the transfer with microwave. This has to be an unpaired electron. Yes.
In the same area.
It does not have to be the same molecule. So that is why DNP is applicable even to system where there is no paramagnetic state. So even if I have a diamagnetic molecule, I can do a DNP transfer. I can do a DNP transfer to even water. Yes, the transferring agent has to be paramagnetic. So depending on application, if someone wants to do DNP for MRI application or solution state NMR application, this is how the setup looks like. If someone wants to measure DNP for solid state sample, this is how the DNP setup looks like. It's basically NMR with a few add-ons. And the add-on can be predicted from the experimental conditions for DNP. So most of the conventional NMR experiments, they are done at room temperature, but DNP happens efficiently at lower temperature. So the temperature range is typically from 1 to 100 Kelvin for DNP. So if someone is doing DNP MRI, the DNP is done at 1 Kelvin, and whatever you are hyperpolarizing, it could be a metabolite that is quickly melted and injected for in vivo scanning. Or if someone is doing solution state NMR, again, you do the DNP, hyperpolarize the sample at 1 Kelvin, quickly melt the sample, and then do the solution state NMR. For MRI, yes, people have hyperpolarized pyruvate, a few other metabolites, and injected into human for in vivo imaging. So human does not have to be at 1 Kelvin, just the metabolite, definitely.
After injecting it, basically thermalizes with the human body.
Yes, exactly.
The process, it retains the hyperpolarized.
So that's a very good point. Once things are hyperpolarized, it will not remain hyperpolarized. It will come back to the Boltzmann equilibrium.
Sure, that's what time scale.
So that is something that people are trying to improve. Right now, the time scale is about a few seconds.
So how are you injecting this into human beings and then reading this up from 1 Kelvin? I don't believe. I'm sorry. That's
No, so that is why this technique of hyperpolarizing and injecting very fast, it is patented by GE. So at some point of time, GE had full control on technique, but there are challenges. So people are trying to solve these challenges. Definitely, it's not possible to retain hyperpolarization for a very long time, and it's not possible without a specialized setup to do a very fast transfer. Even if you do.
So, but what does the specialized setup do?
So one thing is to quickly melt the sample. So the sample, the metabolite is at 1 Kelvin. It is quickly melted and injected in a certain magnetic field such that there are no level anti-crossing. You don't want the polarization to be dispersed. You want polarization to remain on the spin which were hyperpolarized. So there are definitely techniques involved in doing it in a way that we don't lose polarization quickly. But for the case of solid, for magic angle spinning NMR, one does hyperpolarization and measurement, NMR measurement, in the same instrument. So we don't have to shuttle the sample. And it has its own advantage because one can do phase cycling, one can do 2D NMR, like the way we do a conventional NMR can be done in the solid state. So the temperature is about 1 to 100 Kelvin. Magnetic field is from 3 Tesla to 14 Tesla. And the microwave frequency that is needed is resonant with the magnetic field. So the range for this magnetic field is from 90 gigahertz to 400 gigahertz. So this is actually a challenge, like having a source of microwave, high power, high frequency source of microwave is a big challenge. So that is why to create such microwave, one needs to have a special source of microwave. For the case of high field solid state DNP, we use gyrotrons for DNP.
I'm just trying to understand this. So you have this machine patented by GE. So it produces this something and it injects it on human body. But you also tell us that it's thermalized in few seconds. So the NMR has to be performed within that few seconds.
NMR has to be performed. NMR or MRI has to be performed within a few seconds. So this is a limitation.
But this has been done.
This has been done. There are many papers on this technique. It has not reached clinical applications yet. So at the moment, it's just at the research level. But for solution state NMR, this has become very widely used technique. Yes.
Is there any numerical statistics, like if you start with n number of molecules and after a certain time, how they involve, like the time evolution of the states, like you have any kind of model prediction of that
states,
that you can use to like improve the things, like started with n number, how many will evolve after certain amount of time, statistically speaking?
When you say evolve, what exactly do you mean? Evolution?
Like the polarization is changing,
Oh, the
polarization is changing. So at what fraction or something, you have any statistical model?
So I have a slide on that. I'll come back to that.
Yeah, please.
Okay. So this is just to summarize what is DNP. DNP is a technique which is trying to combine the best of NMR and EPR. EPR is very sensitive but does not have resolution. NMR is insensitive but has resolution. So DNP can be thought to be a marriage between NMR and EPR, ideally. I don't have any slides on applications of DNP because that's not exactly my research, but this is to show you the overview of what applications people have been able to achieve with DNP. With DNP, it's now possible to study a lot more nuclei which were not studied without DNP. So those insensitive nuclei can be studied, for example, calcium 43, oxygen 17 at natural abundance can be studied, platinum. The power of DNP can be understood with this spectrum. So basically there are two spectra overlaid, the red one and the blue one. The blue spectrum is acquired in 1 minute. And the red one, to get a sensitivity like the blue one, for the red technique, for the red spectrum, it will take 15 days to have the same level of signal to noise. So this is the power of DNP. Sorry. There's a lag. So we can boost sensitivity. People have now been able to study cell. We can directly hyperpolarize the constituents of the cell, and then we can boost again sensitivity by orders of magnitude. It's possible to study surface. We can selectively hyperpolarize, amplify the signal on the surface and study them. Or you can get NMR signal from constituents which are in very small fraction. So many things which were not possible without DNP is now being done, and DNP is a lot more useful for materials than for biosolid for one reason. And that reason is, if you see this spectrum, there is very low resolution. That is because DNP is done at around 100 Kelvin. So there is a lot of heterogeneity because of conformational trap. So DNP for biosolid loses resolution, but for materials, it's not a big problem. So at the moment, DNP has a lot more applications for studying materials than biosolids.
The surface, can we solve the radical of the surface? So it's no more the same surface. So the normal NMR of the surface versus the DNP NMR. So the chemical shape, the signature, the shape, everything can change, right? Because of the presence of the radical. So there could be deshielding, shielding, all of those effects. So yes, how do we know that it is the same signal?
So it does not have to be chemisorbed on the surface, and the reason will come because there is a thing called spin diffusion. So even if the radical, I'll come to that slide.
Okay.
Before I go to that slide, I'll tell fundamentally, like there was a question, how does DNP work? So fundamentally, it works through a spin flip-flop process. So there is an electron spin, and this is a polarized, it's along the z direction of the magnetic field, and then there's a nuclear spin against the magnetic field. When we shine microwave, we want to shine microwave at a specific resonance condition. So this is a two particle 4 energy level diagram. And what we want to do is we want to induce the flip-flop process. So imagine the green is up, red is down. We want to induce a transition such that it causes a flip-flop of electron and proton. So now the electron is down and the proton is up. If we can induce this transition, quantum mechanically, you would know that this transition is forbidden. It's a zero quantum transition, or it could be a double quantum transition. So it's a forbidden transition. That is why one requires high microwave power to have this transfer happen efficiently. So the microwave has to be resonant to the energy gap between these two states or the energy gap between these two states. So DNP can happen with any material that has unpaired electron. We can use that for DNP. And these are some of the common examples that are common polarizing agents which are used for DNP. It could be a tempo radical, carbon-based radical. It could also be through biradicals, two radicals chemically tethered. It could also be through spin defects in materials. For example, diamond, it has a defect called NV center that can be used for DNP. or other materials like HBN. One can use metal complexes, or one can use chromophores, optically excite those chromophores, and then do DNP with those chromophores. One more slide on the mechanism. So this is example of, say, a radical system. So there is an electron here. And then around electron, unpaired electron, there would be nuclei. For example, there is a proton here. And if these are close enough, here the distance might be a few angstrom. If they are close enough, then we know there would be a hyperfine coupling. It's basically the coupling, dipolar coupling between electron and nuclear spin. So there is this hyperfine coupling. And if this molecule is placed in a magnetic field, there would be Zeeman interaction for the electron spin and for the nuclear spin. For DNP to happen, we need to have these combinations. We need to have microwave, which is at the right condition with respect to Zeeman interaction, and we need to have hyperfine coupling. And if we work out maths, then we would know that it will generate a flip-flop between the electron and nuclear spin. Now, coming to the time scale, what would be the time for which I should irradiate with microwave such that we are able to amplify? And this is actually one of the limitations of DNP at the moment. Depending on what we are doing, what sample, what polarizing agent we have, what's the target analyte, this time scale can be very long. In the green is the time scale of NMR measurement. NMR, you can measure one single scan in a few milliseconds. But before we do NMR, we do DNP, and this build-up time can be very, very long. If things are perfect, it could be just a few seconds, but in many, many cases, it is several minutes. And during this time, the polarization on the nuclei, on the nuclear spin, it actually builds up. So, in today's talk, I'll talk about 3 ways or 3 areas where one can improve things and make DNP faster and more efficient. How we can reduce this time from a few minutes to just a few seconds or a fraction of a second. So that would be the topic of today's talk. So one can control spin diffusion, make spin diffusion faster. One can have a better microwave manipulation. And then one can do also optical pumping to improve the efficiency of DNP. So I'll touch upon these 3 areas. Now, there was a question, how does DNP happen? Suppose someone is interested to measure DNP of a cell, and this does not have unpaired electron. One can induce unpaired electron, but it's going to be very challenging. So even without inducing radical inside the cell, it's possible to do the DNP. And the answer comes from spin diffusion. So for doing DNP of such a system, we would have to have a polarizing agent, and that polarizing agent would have a nuclei very close to the electron spin. What we do is we shine microwave on that electron. There is a small lag. So when we shine microwave, the flip-flop between electron and nuclear spin, that would be activated. Then what would happen is this nuclear spin is talking to another nuclear spin. There would be flip-flop between the 2 nuclear spins now. And this flip-flop process will continue to the bulk. So once we induce the flip-flop between electron and nucleus, and if the 2 nuclei are coupled, the 2 nuclei can flip-flop. And this process can happen in the bulk. So eventually, after a certain time of irradiation, one would see there is flip-flop process and the polarization will diffuse to the bulk. So even if the target molecule is not close to the radical, we don't have to implant the radical on the surface. even if it is far apart, because of spin diffusion process, the polarization can spread from the radical to the target analyte. So one can think of polarization to be distributing, to spreading like an onion shell. So this is what happens, but there is one caveat here in this spin diffusion process. So overall, what I have said so far is DNP involves two processes. There is a transfer from unpaired electron to the nearby nucleus, and then there is a spin diffusion from that nearby nucleus to the bulk nuclei. So there is a diffusion process and there is a direct DNP process. The caveat is, if you make one process efficient, the other process becomes inefficient. So if one would want to make the DNP transfer efficient, this process very efficient, the spin diffusion process becomes inefficient. Then because of streaming, it's a little slow. So there is and this problem is well understood as spin diffusion barrier. And it can be understood in a way that spin diffusion happens between two homonuclei. If two nuclei, they are similar, they have similar energy level, they can flip-flop. The energy is conserved if there is flip-flop. But because one nuclei is strongly coupled to the electron than the other one, the degeneracy is lifted. They are no longer homonuclei. And this causes a diffusion barrier. So in order to make the bulk DNP process efficient, one has to overcome the spin diffusion barrier. So in next 2 or 3 slides, I'm going to talk about how we can make spin diffusion faster. The answer is, if we can have multiple electrons talking to each other, if we have more electrons talking to each other, then the coupling between two electrons, it can help to overcome the spin diffusion barrier. And this can be understood. It can be understood using the energy level. I'll not go into the details, but if we have two electrons coupled and say there are two nuclei, the flip-flop of the two nuclei, it depends on the coupling between two electrons. Because there will be a simultaneous 4-spin flip-flop mechanism that would be activated for this scenario. And what we can see here is these plots, they show the flip-flop between two nuclei. On the left-hand side, when the coupling between two electrons is weak, the rate of flip-flop or polarization exchange is slow as compared to if the coupling is strong. So by having strongly coupled electron spins biradical, it's possible to have faster spin diffusion.
Is there a parameter to look at how much efficient the polarization transfer is, or how many molecules can compass?
For example, as you, is there a parameter to qualify that?
There are parameters, but a lot of time, many parameters, they are convoluted.
Okay.
So it's very hard to identify one problem. One can do numerical simulation and model it.
Right.
But
Something what Prajalak was asking about, how much fraction would you transfer?
Since experimentally we don't measure the nuclei which are directly coupled with electron. We measure the bulk magnetization. So experimentally, it's very hard to deconvolute different factors. It's a very good question. First answer is to make the technique more versatile. Not every molecule that you would be interested to study in NMR would have unpaired electron.
No, that's okay. You add the unpaired electron, but you're also transferring this entire polarization solvent and then recording it. So I will not add the solvent, just the material, the surface, and your radical, and record the DNP. What would be the effect?
So one disadvantage would be paramagnetic broadening. So if we do NMR of systems which has too many unpaired electrons, then that electron will bleach the nuclear signal. I'll not go into details, but this spin diffusion picture is actually valid even for magic angle spinning. When we physically rotate the sample, the energy levels, because of anisotropy, these electron spins, they have anisotropy. So the energy levels oscillates periodically. And there will be scenario where there are two energy levels, they are almost degenerate. So there would be level crossing. And we can see here is every time there is a level crossing between two electrons, they flip-flop. And the flip-flop of two electrons also causes a nuclear spin flip-flop, which is indicated as a rise in the polarization of the nuclear spin. So this is applicable. This is, so far I have shown theoretical stuff, but the technique, the principle is actually also valid experimentally, which is tested here. So when we compare biradicals with two different distances, a biradical which has shorter distance or stronger coupling leads to faster buildup. And even for monoradicals, if we concentrate the radicals such that the average distance is shorter, then the buildup time becomes faster. So now we have a new design principle for narrow line radicals. Instead of dealing with monoradicals, if we can have a chemically tethered biradical, it can lead to faster spin diffusion. So this was first part. Now I am moving to the second part, which is about microwave irradiation. So most of the time when we do NMR or EPR, at least when we do NMR, we do pulsed NMR. No one would be doing now CW NMR. But DNP at the moment is very primitive. Most of the time when people do DNP experiment, it's CW DNP. The microwave is continuously on. So the idea in the field is to move to the regime of pulsed DNP. So I'll spend a few slides on pulsed DNP. Effectively what we want to create is we want to create a unitary transformation which can flip-flop the alpha beta and beta alpha state.
The EPR community has been doing this on the reverse side,
yes.
like NDOR or PELDOR.
Yeah.
So this has been done by the EPR community,
but
very routine.
Yeah, that is at very low magnetic field. So now the idea is to push it to higher magnetic field. So again, this is the setup, and which is used commercially. It's a commercially available setup. It's used for doing DNP. This source of microwave, it's a continuous source. So we either turn on and off the microwave. You cannot do pulsing with this setup. In order to increase the efficiency of DNP, one has to go to the pulsed regime. So the microwave irradiation has to look something like this. It should not be continuous. It has to be shaped, pulsed. We might be able to change the phase of the pulses. So this is what we would want to do to have better transfer efficiency. And recently there is a lot of interest in developing these techniques. I'll show you one of the approaches. So these are the three most popular pulsed DNP scheme. The top one is called novel. Then this is called TOP or time optimized pulsed DNP. This is called XIX DNP. So these techniques, when they were developed, although the development is very recent, but when they were developed with respect to a single electron. Because for a single electron, the energy levels are easy to, so one was able to optimize these pulses for the single electron. And we saw that when there is a single electron, the spin diffusion is slow. So what I am showing here is the efficiency of these techniques as a function of electron-electron coupling. When the coupling is weak, they are efficient, but as you increase the coupling by shortening the distance between two electrons, it becomes more and more inefficient. So all the pulse DNP techniques which were developed until very recently, they don't tolerate the electron-electron coupling. What we have recently worked on is to improve, to overcome this limitation. And the reason why electron-electron coupling interferes, it comes from the fact that the Hamiltonian for electron-electron coupling does not commute with the Hamiltonian for electron-nuclear coupling. So if two things, they don't commute, they interfere each other. So that's the basic idea. So we wanted to overcome this. And the answer, we found that one of the answers to, one of the way to overcome this, this limitation is very simple. Actually, what we have to do is, we have to do something called magic, effective rotation at the magic angle. So those who have done solid state NMR, they would know that whenever solid state NMR is done, the sample is rotated at the magic angle. It's rotated at an angle of 54.7. Compared to that, novel, the rotation is in the transverse plane. So one way to overcome this electron-electron coupling limitation is to do an effective spin lock at the magic angle. So if we do the effective spin lock at the magic angle, we can see the technique magic novel is efficient even for shorter distances between two electrons as compared to simple novel. In novel technique, the moment you have electron-electron coupling, the efficiency goes down. But here the technique remains efficient up to 15 angstrom distance between two electrons, 1.5 nanometer. And this concept is applicable even for other techniques. So one other technique which is used in pulse DNP is called pulse pole. Pulse pole is very robust to the detuning. So here is a comparison to the efficiency. Red is the pulse pole technique and the blue is the novel technique. In novel, the moment you deviate from the optimum parameter, there is a drop in the efficiency. But pulse pole is very efficient. So we thought of implementing or improvising upon pulse pole such that it can be tolerant to the electron-electron coupling. And here is a comparison. So if you have normal pulse pole, the efficiency goes down the moment we have electron-electron coupling. But we came up with a variant of pulse pole which we named magic pulse pole. And here, which includes basically some phase cycling and adding some compensation factor. You can see the efficiency, which is the maximum transfer. It remains almost as efficient as the technique being based on a single electron. So even if we include the electron-electron coupling, the transfer rate to the neighboring nuclei is very efficient. Yes.
But then why is it dependent on, I mean, it should be respective whether it's the continuous wave or the pulse, right? Why is it dependent on when you are pulsing, the efficiency is going down, but seems to be not matter?
When we are pulsing, we are using a different method slightly as compared to continuous wave. In continuous wave, one uses a technique called solid effect DNP, where the irradiation is at a certain offset, and that offset is nuclear Larmor frequency. So that's a different way of transferring as compared to pulsed technique.
I see. So maybe it's...
Yes. If you see the final Hamiltonian, the final effective unitary transformation is the same, but how do we reach to that effective Hamiltonian? That is different for CW versus pulsed technique. Since in CW, we cannot have more than one frequency, we cannot have more than one phase, but in pulsed, you can change the timing, you can change the phase, you can change the amplitude. So this technique is based on, if you see, these are all the pulses. Every colored bar is a pulse with different length, with different phase.
I see. Okay. Yeah. But I mean, I would have assumed that, you know, it would be same for your continuous wave as well. I mean, if you put two electrons, the transfer will go down.
It's different because you can think of, if you are doing continuously, you always have one Hamiltonian, but here we have constructive and destructive Hamiltonian. We can select something and we can destructively, we can cancel something in the pulse technique. In the CW technique, it's not easy to do that.
That is then dependent on your pulse. So it is not, it cannot be a generic statement. It will depend on the pulse profile that you're putting.
Yes.
So you have to just construct the pulse profile properly that gives you some.
Exactly.
I mean, I don't know the details of the Hamiltonian right now, but that gives you a constructing interference. So I think you made a generic statement that the pulse doesn't give you.
Yes.
So that cannot be a generic statement, right? Is that correct? Or?
So yeah, whatever you said is correct. So for example, this is the pulse pole technique. These pulses, these sequences of pulses, they don't cancel a certain term, which leads to deleterious effect. Nice. But the other sequence, that the one we have here at the bottom, it cancels that deleterious term. And it could be different for different pulse technique. If you want to improve it, there is not single recipe. One has to look at the effective Hamiltonian. How does things change? How much time do I have?
Yeah.
Okay. Okay, I now move to the final part of the talk, which is how we can use optical pumping to improve DNP even better. And what are the areas of improvement based on conventional technique? There are several limitations of DNP. There are many limitations of DNP. One of the major limitation, in my opinion, although the technique has been there for last 20 years, but still has not been very popular. And the reason is cost. In last 20 years, there has been only 53 setups across the world. There is no DNP in India. There is no DNP in many of the neighboring countries because the setup is very expensive. And maybe one requires very good training to be able to operate DNP as compared to NMR, where NMR has matured enough that one can use NMR, run NMR without having a PhD in NMR. But DNP at the moment is not like that. So it's very expensive technique. And there are other limitations. I'll not go into that. But one of the other limitations is when we do DNP, we are using thermal polarization of electron, which is not unity. So if you look at the polarization of electron, it's only about 1%. What does it mean? It means that if someone takes 100 electrons, only 1 out of 100 electron is effectively giving us DNP. So the polarization to begin with is only 1%. Nucleus, definitely it's much less than 1%. It's 3 orders of magnitude lower. But if you look at the electronics energy level, the polarization is almost unity. So that's why at IR, UV waves, they're very sensitive, but NMR is not. EPR is less sensitive than these electronic techniques. So the idea is, can we pre-hyperpolarize the electron spin? Can we, just like we hyperpolarize nuclear spin using electron spin, can we hyperpolarize the electron spin by making use of the electronic states of the molecule?
Measurements on the field, then is it not like most of the population will be in the ground state for the nuclear spin in that case?
Yes, you're right. If we are at 1 Kelvin, then we have almost 100% polarization on electron. But if you are doing something like magic angle spinning DNP, it's not possible to physically rotate the sample at 1 Kelvin. People have been able to rotate the sample down to 20 Kelvin, but it's very expensive. It's a lot more expensive technique because you use helium to rotate the sample at that temperature. So every day it would cost 100 liters of helium to be able to physically rotate the sample at that.
So for higher temperature measurement?
Yes, for higher temperature measurement, one requires some alternatives.
Right.
So if one can have higher polarization, even without going to the lower temperature, that would be a big boost for DNP. Conceptually, it's possible to do that. And there are many molecular systems, crystal systems, which can hyperpolarize electron spin. It can be done using some light activated, for example, UV irradiated radical, or it could be using systems that would generate radical pair or a triplet, or it could be a combination of triplet and radical or 2 triplets. So conceptually, there are many molecular systems which can help us achieve electron spin hyperpolarization, which can be relayed to the nuclear spin. We would. Yes. So it would become less versatile, for sure. True. So right now the technique has not matured enough that one would think of those problems. But at the moment, people are trying to just use them in some basic solvent, and people are trying to improve the signal of the solvent themselves. But yes, there could be interference. The irradiation of these chromophores can also change the ground state of the molecule, target analyte, all those problems would be there. So there are many ways. One of the, like some 10 years ago, people got really excited about using diamond for this. Because diamond have okay. So diamond basically acts like a spin one system. And here one can shine green light, and shining green light will initialize the electron spin to almost 100% polarization. So diamond is a very good system to hyperpolarize the electron spin, even at room temperature. With a very simple setup, one can use LED, shine LED, and the electron spins in the diamond would be highly polarized. But there is a problem, and that problem is the polarization does not come out of the crystal. So if one brings a protein on the top of diamond surface, the protein is not hyperpolarized. The small organic molecule will not be hyperpolarized. The surface, I'm not too much into the diamonds, but those who have studied diamond, they say the surface of diamond is not clean. There are a lot of dangling bonds, and that causes fast decoherence on the surface. Although inside the coherence time is very long. So we are excited about diamond for other reason. One can do some nanoscale studies. One cannot get the structure of the molecules, but can do some relaxometry on the surface. So for those applications, we are building up a setup for diamond magnetometry, which will not be competing with NMR, but it can give some complementary information. So, but for hyperpolarization, diamond at the moment does not seem very exciting. What we are doing is, we are thinking of other molecules whose energetics would be similar to diamond. The idea is, can we optically pump some molecules and create a hyperpolarized electron spin state? Theoretically, it is possible to do that. We tried many combinations of chromophores coupled with radical system. And finally, we came up with, since I'm running out of time, we came up with a system where there is a PDI coupled with BDPA radical. And here, if we shine green light, this BDPA radical gets optically hyperpolarized. Just by shining light for a few milliseconds, it's possible to hyperpolarize the electron spin in the BDPA. And the polarization lifetime is hundreds of microseconds, or several microseconds, which is enough to do a relay transfer to the nuclear spin. This was done at 85 Kelvin. But there are molecules which are not very efficient, but they can hyperpolarize even at room temperature. We used EPR to do this experiment. And for the EPR, we did not have that time NMR measurement. So what we have shown, just as a proof of concept, we have shown that the hyperpolarized electron spin can do the DNP transfer to the nuclear spin. So whenever we match the DNP resonance condition, we see a dip in the electron spin polarization. And then that polarization can be stored on the nucleus, and we can transfer it back to the electron. So, and this whole process is very coherent. So this is something which has been done conceptually, although we don't have any application and it has to mature a lot more. We have now other molecular design. We have other chromophore coupled with radical system, monoradical, or chromophore coupled with biradical. So these are the molecular systems that we would be exploring in future. So there is diamond, there are these triplet molecules coupled with radical. The other system which has become very exciting recently is radical pair system. So molecular system which can generate spin correlated radical pair. And this is one of the recent examples from Lyndon Amsley's lab at EPFL. He showed that a molecule like this, which has a chromophore and a donor and acceptor of electron, when we shine light, just by shining light, it's possible to hyperpolarize the NMR signal, just shining light. And this could be a game changer if it works efficiently, because you don't require any microwave here. And one of the most expensive component of a DNP spectrometer is microwave, high frequency, high power microwave. So if just by shining light one can hyperpolarize, that could be a very good thing. So as a proof of principle, he showed in 2023, that one can hyperpolarize the NMR signal. And then more recently, he came up with another molecule which can hyperpolarize even more efficiently. We did not have our setups ready then, so we thought of understanding how it is working. And what we understand so far is, when these molecules are optically excited, it goes into an excited singlet state, and it can do inter-system crossing with a triplet state. And this process, there could be different ways of inter-system crossing. One of the ways involve nuclear spin. So if there is a nuclear spin also nearby these spin correlated radical pair, the nuclear spin, depending on the parameters, the nuclear spin can be hyperpolarized through a 3-spin mixing mechanism. Yes. Since I'm running out of time, I'll not go into details, but what we have now is we have a precise matching condition, which is shown here. We have a scaling factor, which determines how fast this 3-spin mixing can happen. And we have an intensity factor, which is like how efficiently it can happen. So we have an exact condition. And if you see here, there are two plots. One is analytical, other is purely numerical. And we have one-to-one match with the analytical and numerical predictions. This is applicable not just for a specific condition, but even this is for a contour. So as a function of different parameters, we have one-to-one matching when matching for the 3-spin mixing. When would that 3-spin mixing lead to nuclear spin polarization? What was most exciting at the time we were working on this is the same spin correlated radical pair singlet triplet conversion using nuclear spin. The same mechanism has been proposed to be applicable for magnetoreception. So many of the things that I have shown today is based on some theoretical research that we did in the last 2 years. But now our lab is equipped with several instruments. So we have definitely solid state DNP. We also have pulsed EPR, which is coupled to a nanosecond pulsed laser. Then we have NV sensor. And at the moment, we are building up another DNP system, which can go down to 2 Kelvin, and it can also go up higher to higher temperature. It can have a variable magnetic field. And this is very much needed because most of the time, commercially, when people do DNP, the gyrotron, the source of microwave, is fixed. And that is fixed to nitro oxide. So electron spins whose G tensor is close to 2. If you come up with another system whose G tensor is 1.8, commercially available setups would not be able to do DNP. But if we can sweep the magnetic field to be in resonance, then one can do DNP with any of the systems. I think somehow my laptop.
Your laptop.
Yeah, I'm sorry.
It just died.
I think just restarting. No, power was there. So, but this was very much the end of my presentation. So it's possible with the setup that we are building, it's possible to do DNP for any system, almost for any system, and we can also do optical irradiation there.
Okay.
So let's have few more questions to Asif, and we can conclude. Yes.
Instead of organic dyes based polarization, can one also use inorganic dye, like say quantum dots? You excite, get the excited electron, and then use that to transfer the polarization.
Yes, it's possible. I'm not sure if someone has already done that, but it's possible to do it with quantum dots.
We tried something with the defects in the silica, but it did not work out. But there could be some other materials.
So the microwave has to penetrate. That's one thing. The relaxation of electron spin should not be too fast.
No, I'm not talking about microwave. The other work where you don't have a microwave, just excite by the laser and.
If we just excite by the laser, then we don't know what's happening upon excitation.
Yeah,
in
that's
our
another
own
question.
case, we thought of different molecules, chromophore radical. Out of 10 molecules, only one of them work. So the understanding of how exactly the polarization transfer happens in the excited state I think it's not understood. What I showed is just for the very specific case where we generate a singlet, where we generate a radical pair, and if there is a nuclear spin, what can happen? We have a prediction on that, but there are many other molecular systems, we don't know what would happen.
I have a quick question. Maybe let's
rephrase. So this temperature dependence that you have, it only is because you need the polarization, right? 1 Kelvin works best. But does that also limit the transfer? So is the transfer mechanism also temperature dependent?
By itself, it's not temperature dependent,
right?
But there is one factor, which is relaxation.
Right.
Relaxation depends on dynamics.
Right.
Dynamics depends on temperature.
Again.
So if temperature is making relaxation very fast
or slow,
or very slow,
then it's also a problem.
Very slow, but normally in the current regime,
yes.
It's the fast relaxation which is the killing factor.
Right. Okay. And the other question, and these are some ideas also in the singlet fission community, it exists that you can have these two triplets, a triplet state, right? And that can also sort of create hyperpolarization on the electron, and then that can be used, just like your donor acceptor case where you have spin correlated radical pair. Has that been explored also?
There is a Nature Communication paper which is based on anthracene, if I'm not wrong.
Or pentacene, maybe.
Yes, where they showed using a quintet system, you can hyperpolarize nuclear spin.
At room temperature, because you can generate, in certain cases at room temperature, you can generate these states.
This I'm not sure if it was done at room temperature. Theoretically, it's possible.
The quintet states have been generated at room temperature. So that can enable
that can enable. The lifetime has to be long enough. There could be one advantage of quintet state is it's a spin 2 system.
Yes.
So the effective nutation that we get on electron spin is higher than spin half system.
Yes. Okay. Any other question for Asif? If none, let's thank Asif once again, and let's take the walk to West Canteen together, and we'll have some snacks there. Thank you, Asif.
Thank you.